gonna talk about scaling off-chain with state channels, which is pretty hot topic, I think. He's one of the first commercial users of Erlang from 1993. In 96, he joined Ericsson and became the chief designer of the AXD301 development, which is arguably one of the most complex systems ever built on Erlang. So he's actually, by the way, a very active member of the open source Erlang community. And I think Ulf Wiger will carry on. So please give him a round of applause, guys. Guys, come on.
Hi. I can actually see you.
It's magic.
That's probably a good thing. Okay. I'm going to be talking about scaling. I hope I'll be able to give a slightly different spin on the topic. He told you most of this already. I spent some of my formative years in Alaska working on disaster response, military command and control. One of the nice things about that, or nice, however you want to put it, is that if your software breaks, people die. It's a sobering experience. So it teaches you to try to stay pragmatic and remember that your designs may have consequences. So anyway, in that scenario, I came across Erlang, fell in love quickly, and actually then paid $1,000 for a commercial license back in '93, which seems like it would disqualify me as an investor. I'm one of the few people who have ever paid for Erlang, I think. So anyway, Ericsson, I was CTO for a while, Erlang Solutions. Lately, I've been more of an entrepreneur, freelancer, software, and opera singing, actually, so to diversify a little bit. Okay, so I'm going to talk a little bit about what I mean with scalability in this context, and then give you a little introduction, blockchain introduction, unless you, in case you need that, and talk a little bit about what issues we're trying to address. So basically, it's simple with scalability. If I add X, I should get more of Y. But what exactly is it? Oh, it didn't update. I thought I added another slide here. Anyway, that's what you get when you update in the last minute. Yeah, but it's a Google Docs link. I thought I could do that. So anyway, no. It was just. So the important thing is to keep your eye on what it actually is you want to unlock. And in our case, you could think of scalability as actually getting more types of use cases, more applications on the chain, more users. Now, that will translate to higher capacity demands on the technology, but that's not sort of the key thing. The key thing is, what does it enable? And so you can think of a couple of different use case classes and think about what are the boundary conditions for those. And so a couple of examples here, just to keep in mind. You could have like an online rental service. The world needs more scooter rental services. Pay for coffee is sort of the classical example. Maybe have a tip jar. For example, on social media, you can click on a button to clap hands and stuff. It doesn't really put food on the table for the guy who actually put effort into creating something good. You could actually, instead of clapping, put some tokens in there. That's a use case. Pay to read actually exists. Usually you will there will be pages that want to tell you a story, usually uninteresting. The interesting part for them is that they flood you with ads on every page. So they give you a paragraph, and then you have to click next, and then you see a ton of new ads, and that concept could possibly be improved. But you could say that it beats a paywall that gives you a useless abstract and then says pay 70 euros to read the rest. So these are a couple of applications that we can think about. Oh, there it was. Okay, so we often compare to Visa. It's like we want to be the new Visa. It's a bit weird. Visa is very trustful. I mean, you trust Visa to do the right thing, but you do get throughput. This is a log scale, so if it wasn't, then we'd hardly even see the other the bars there. But also, if you think about how blockchains work, if we would have that kind of throughput, we'd have an issue with blockchain size that we would have to solve very quickly. You can see that aeternity is not bad as blockchains go. We have Bitcoin here at 7, basically Ethereum at 20, aeternity at 100. Woo! Almost PayPal class, and Visa out there. But we also have responsiveness. That's been talked about a little bit. You have here, for example, first confirmation. This is not a log scale, and a big bar is not good in this case. So Bitcoin, you have 10-minute block intervals, so you may have to wait 10 minutes to see if it even got on chain to begin with. Ethereum, about 15 seconds. Eternity, 3 seconds. Visa, just winging it. How long does it take for a credit card transaction to be approved? Not many seconds. But then you also have finality, and this is a log scale. So when can you actually trust that you got the money? Visa, well, when it starts printing out the receipt, you know. Bitcoin, what do they? Normally they recommend 6 block confirmations. That's a long time. Ethereum, 20 to 40, perhaps. Eternity, I don't know if I said 6 there. But anyway, now we're talking enough time to get people behind you in the coffee queue a bit annoyed. So then what happens? You go 0 confirmation. In our case, that would be basically this, microblock confirmation, 3 seconds perhaps. Then at least you know that some miner felt it worthwhile to put it in a microblock. So at least it wasn't immediately invalid or rejected. But you still have to wait in order to know that it really got there. So this is a problem. So, enter state channels. Now we're going to introduce some symbols here for our modeling work, where the iconic Alice and Bob and Mario gets to represent the miners. So, and we deal with coins, transactions, signatures, and blocks. And the chain is a series of blocks, as you know. Now, Alice wants to pay for coffee, and Bob wants to serve coffee. Now, on the blockchain, it doesn't really work like that. Alice has to send a transaction to the crazy miners. Hopefully, it will eventually make it onto the blockchain, and then you have to wait a couple of blocks, and then the coffee is cold. So, one problem there, like we said, either you have to wait for confirmation, or you have to trust Alice. And the other thing also is that we actually pay transaction fees. They're not very high on Eternity, but and so these are not really micro payments. And if we want to do contracts, we have got high gas costs. So this is just generally payment channels. You go off-chain, you basically reserve some funds off-chain in like an abstract data type, you have balances. And then if you disagree, you have to go on-chain. And then there is a protocol for resolving a dispute so that you can get your coins back. So in this case, hello? Okay. I'm clicking. Okay, anyway. You open on-chain, you need an on-chain transaction to open the channel, and then you close on-chain. I'm not going to go back and do that again. And then while you're off-chain, you can do lots of transactions very quickly. So as long as you're off-chain, everything is nice. You can buy lots of coffee, and you can come back for more, and Bob is happy. So aeternity, we built these state channels. Actually, state means that you can also execute contracts. So the channel has state, not just balances. We can also use generalized accounts. And Dimitar could tell you all about the fun times of making that work with state channels, but that's not what his talk is going to be about. But as we do in aeternity, state channels are first-class objects on the chain. And there is a documented protocol for disputes. There is a protocol for the handshakes. We think that this is both clearer and simpler than very complex contracts on Ethereum, for example. And we also think that it's cheaper, because since we actually have these transaction types on-chain, we can both be safer and faster. Now, the on-chain transactions that we have in aeternity, you can create a channel that's a special transaction. You can deposit more funds. You can withdraw funds. You can do a snapshot. That's basically, in case of disputes, you're doing off-chain transactions, you can actually pay for getting a snapshot, whether the other party wants to or not. So it's like a backup on-chain. So then you know that at least that state will be something that you can enforce. You can also force contracts to progress. So you're playing chess, the other guy knows, or Bob realizes that he's going to lose because the next move is the winning move, and he bails out. So Alice could then actually execute the winning move on-chain and get her profit. And then we have mutual close and solo close and all that. So that's kind of the life cycle. You create the chain, then you do your off-chain updates. They never touch the chain unless you deposit withdraw, like we said, and then you close it. Now, introducing a new character, we actually have what some people lovingly refer to as the FSM. That is doing a lot of the complex work. So Alice uses a WebSocket interface, perhaps, and tells, that's the Cheshire cat, unless if someone is wondering. So she tells her FSM that I want to pay Bob 2 tokens, and the cat says, okay, sign this. Alice signs it because only she has the key. And then it's sent over to Bob, and he is asked to sign. He replies with the signature, and then Alice gets confirmation. So that's the flow. And here you have immediate confirmation. And the co-signing indicates that you now agree to a new state and a new balanced distribution on chain. And then we have these different closing semantics that I'm not going to talk about. Now, performance, since we're talking scalability, is a bit interesting. These are basically numbers from our system or our integration tests and unit tests. We have the first one, we have a single channel, and then we're just running a busy loop where we're transferring a token back and forth. So we can do that on my reasonably okay laptop. I can do more than 100 such updates per second on one channel. That's pretty decent. We have another where we throw up 10 concurrent channels and we tell them all to do the same thing. And then in total, my laptop can push through at least 400. I don't remember the exact number. It varies a little bit depending on what we do with the code. But so if you're running a node, you can service multiple FSMs and hundreds of transactions per second per node in the network. So we add more nodes. This will essentially scale linearly. So then we can talk many thousand transactions going on simultaneously per second in the system. Contract calls are slower, but we also have something we call in-band messages. They require no signing. You're just basically sending a message, and you can send messages to each other. And they take the same path. So you have the ordering is preserved, which is a nice thing. Those you can do several thousand per second. So they're cheap. And this, you can think of this as the things that require signing are the things that you actually have to agree about. But if you're going to send, you want to redraw a game board or something, no need to have co-signing for that, because the state explains what the board should look like. So then you can send messages where you can animate, you could, or say we have the pay to read example where, okay, you pay, that needs to be co-signed, but then you can actually just send the text. So that can also unlock performance. Now, we still have the problem with the channel creation. So if we want to go for immediate micropayments, where presumably Alice is out walking about and she sees a coffee shop that she hasn't tried, so she doesn't have a state channel set up with that particular Bob. So now we're still looking at the confirmation time, where it'll take several minutes to actually set things up so that she can then do a quick payment. So that actually disqualifies state channels for a lot of different solutions, because you can't really do the ad hoc quick transactions. So slow to open, we talked about zero confirmation, not very secure. We don't want to forego security. So how do we do this? We introduce, many of you are probably too young to know who that Ingrid is, but she's as iconic as Alice almost. It's Ingrid Bergman. She represents the intermediary here. So Alice sets up what I like to call a staging channel to Ingrid. And Ingrid can be running a marketplace of businesses, for example. So Bob in his coffee shop, has a staging channel to Ingrid. So Alice finds Bob, they negotiate a channel, and the thing that's different is that instead of putting the channel creation TX on chain, they store a virtual channel object on this staging channel, and that just requires co-signing with Ingrid. And then this channel looks exactly like a normal channel. So the thing that's different is how you represent the on-chain data. It's not actually on-chain. If there is a dispute here between Bob and Ingrid, no, Bob and Alice and Bob, then Ingrid basically is the arbiter, and we run the same dispute logic here as we would on chain. Now, if there is a dispute here, it goes to the next lower level and finally on chain if you can't resolve it. So it becomes a little bit recursive. It's a little bit more difficult to think through all the steps, but essentially it's the same logic. Now, there is a yellow paper. This is not implemented yet. We have a paper, kind of more of a blog post than a specification, but you can read it. It describes pretty much how virtual state channels are going to work. And this is going to be the next thing we start working on after this. So then if you look at what kind of performance you would have at least 2 off-chain updates to create the virtual channel object on both of the state channels involved. There may be other updates, but these would be the ones that are absolutely required. And then to close it, well, okay, if we include the mutual close transaction, for example, on the virtual channel, and then the other 2 closing transactions, so then we're looking at 3 to close it. Now these updates, looking at the performance figures from before, we're talking about 10 milliseconds plus latency. So it seems like under perfect conditions, you should be able to set up a virtual channel, pay for coffee, close it within like 100 milliseconds plus latency plus signing delays. And then, of course, you have generalized accounts, so signing is automatic. And so now we feel that, yes, this ought to be quick enough to pay for coffee, to fill the tip jar, to pay for the next page of that article that you couldn't read before because it was behind a paywall. And those are just the use cases that are easy to imagine. So I guess what we're hoping for is that if we can implement kind of like ad hoc nano payments, then people could imagine a lot of new use cases for that are basically not possible now, because you won't do this with Visa because the transaction fees are basically too high, and they won't help you with it because that breaks their business case. And that's the problem with these micropayments. It's like, well, you want so much speed, and so how do you recover the money? So part of the virtual state channel design is that Ingrid will be able to charge a small fee for replicating the channel objects, and some other designs so that she will be sure to recover her funds in all cases, so that she can actually build a business on this. Yes. So, yeah, for the rental service, I didn't. The speed there isn't really that important, I guess, even though you might not want to stand there and wait several minutes to set up a channel. So before you pick up the scooter. But we have done some other things, because we actually have Alexander, who is sitting in the state channel team and prototyping a service level or server side middleware, if you will, and giving us really good feedback. So we've implemented support for example, generic acceptors, so that you could have your state channel server worked pretty much like your typical TCP server with spawning a bunch of acceptors, and they will then pair with the right FSM, and it will be easier and more scalable. We have the automatic signing support with generalized accounts, which, as Hans said, nobody uses. And then we worked very hard on handling all kinds of cases of communication failure, or the other side crashing, coming back, the WebSocket dying, coming back. This is the work in progress, but it's continuously improving. And this is sort of real world important in order to make the user experience nice enough that people will want to use this in real applications. Yeah, for the coffee shop, we have the ad hoc temporary channels. We have the sub-second confirmation, ideally, and pretty much the same thing in the sort of pay-to-read case or the tip jar. That's, you can have very low fees, very quick response, and essentially nano payments, since micropayments is already sort of used for what's available today, and we think this goes further. Okay, so that was pretty much what I thought I could squeeze into 20 minutes. So I'm ready for questions.
A round of applause first. Thank you. It was actually a good 35, but yeah, we have a first question. Go on.
I have two, again.
As usual.
Yeah. You were speaking a lot about money, but state channels is not only about money. And I wondered how the theory changes when we are talking just about data. For example, when you do gaming. And the second thing is, can you actually extend a little bit the state channel on-chain object to include custom logic? Because when you're not talking about money, the settlement and dispute resolution actually becomes quite different than just accounting.
Yeah, so I breezed over that by basically saying that aeternity state channels are not just about payments. You can install contracts on the state channel. You can execute contracts. Dimitar may have time to talk about that a little bit more. But basically then what you do is you, one side will make a contract call and then take the output and hash the resulting state, and then send that state hash, top level hash, together with the contract call and parameters to the other side. And so that was Alice. Now Bob performs the same call, verifies that he gets the same top hash, and then cosigns it. So then you progress to newer states. And as I said, that was a bit slower. It is slower than just plain payments because you actually have to execute the contracts. And that's also, so we have, so you do have the transfer of funds. You can also sort of do that within contracts. You can lock funds into contracts, which can allow for a lot of different interesting use cases on the channel. And then you can also have the virtual messages, which can provide for sort of dialogue, all kinds of stuff that doesn't actually have to be signed, that leads up to the next transaction that you actually have to agree on. So yeah, you can do a lot of things, and so potentially you could do these things with contracts as well. It's just kind of easier to talk about the payments.
Any more?
Was that?
You want to follow up on that? Yeah? Oh, you have another. Well, no surprise, but you're good at them today. No, go on.
Come on.
Okay.
Yes.
Cool. I think that there is a way to do the virtual payment channels without actually including Ingrid. Have you explored this opportunity just by depositing on a channel or not yet deployed contract that can act as a channel? Have you tried exploring without actually including third party?
We haven't put much effort into it, no. So one of the things about our state channels is that they're essentially conversational, like multimedia sessions almost, if you want. Maybe that kind of betrays the telecom background or something, that you actually have sort of communicating state machines that are doing stuff in real time. So one of the things that we really wanted was to get to that point where we set up a virtual channel and it behaves exactly the same. Now, how we manage the, or basically emulate the chain, I guess that could be done in different ways. So this intermediary thing was partly also because you also want to include, for example, routing. You may think of this, Ingrid may represent, say, a social marketplace where you can find people to interact with. So we think that it's kind of interesting to have an intermediary anyway, kind of a market facilitator side. And also make a solution that provides sort of the opportunity for a business case for someone to provide that market. So that's been our thinking. But if there are other interesting ways to that would give other benefits, then we're certainly willing to listen to that.
Right. I think let's give a round of applause because we have more state channels coming.